In this video, we'll discuss why catalysts are used in reactions. So as per the collision theory, A and B, if they collide, they'll form C in the case if two conditions are met. So the first condition is that the particles should have sufficient energy, which is known as activation energy. So particles have energy in the term of kinetic energy, translation energy, potential energy. And if we look at the energy versus the extent of reaction graph, then if this is the reactants and this is the products, then they should have this amount of energy, which is known as activation energy, so that they can react and form the products. The second condition is that a sufficient amount of collisions occur. So if n total amount of n collisions occur, then only m amount of successful reactions take place. So if we think about it in this way, then if the number of collisions, so n is higher, then there'll be a much higher chance of M occurring, a higher chance of reactants converting to products. So if we have a reaction that is A plus B gives C, then how would we increase the rate of reaction? So the first thing that you could think was that you could change the temperature. So if this is my reaction vessel and these are my particles. Now if in the case of endothermic reactions where you need to give in energy so that the reaction proceeds to completion, if I increase the temperature, now my particles will have more kinetic energy, they'll vibrate more, and there'll be a higher chance of collisions as well, right? And they have more energy that they could give into the they have sufficient amount of energy as well, so now they can convert to the products. So now both conditions are met if we change the temperature. So this is for endothermic reactions. In the case of exothermic reactions where they need to release heat for the reaction to proceed, then you need to lower the temperature. Another thing that you could do is you could increase the concentration of reactants. So in this vessel, there are 5 reactants. Now, if I put in 5 more reactant molecules, now I'll have a higher chance of collision because now the volume is less and I have more particles or molecules that will have higher chance of collisions. And again, I'll be able to increase the rate of reaction. Or you could change the pressure. So like if this is my reaction vessel and I have a barrier like this on which I could put a weight and I could increase the pressure on, suppose if this is a gaseous compound, there are gaseous molecules present, like it's a hydrogen and ammonia, suppose to give, hydrogen and nitrogen to give ammonia. Then if I increase the pressure, now according to Boyle's law, which is P is inversely proportional to volume, now my volume will decrease. So originally if this is the volume and I have this much space, I will reduce the volume to here and I still have the same number of molecules. I have another higher amount of collisions that will occur and I'll be able to proceed faster to completion. Another thing that you could do think about is Lee-Chatterley's principle, which says that if there's any imbalance or inequilibrium that is introduced into the reaction will proceed in such a direction that the inequilibrium is reduced. So now if I think in terms of moles, so if A plus B gives C, if this is a balanced stoichiometric reaction, then there are 2 moles on this side and only 1 mole on the product side. So if I reduce the volume or increase the pressure, then the forward reaction will be preferred and I'll get a faster reaction that takes place. Another thing you could do is lower the volume of the reaction vessel, which again is the same thing here. Like if this is the size of the reaction vessel and I have 7 reactant molecules and this is if I have a smaller vessel and the same amount of reactant molecules, I'll again have a higher chance of the collisions. Another thing you could do is in the case of solid components or compounds, you could increase the surface area. So if I had a block like this and I want to react with another block like this, so only I have this surface area that could react and take place in the reaction. Now if I have smaller blocks of smaller size, then I'll have again a much higher surface area if you think in terms of how many blocks there are. But if I have a powder like talc, now I have even higher chances of collision and I have a higher surface area that takes place in the reaction. The last thing that you could do is another thing that you could do is use catalysts. So what are catalysts? Catalysts are defined as a substance that affects the rate of reaction, but after the completion of the reaction, they remain unchanged. And catalysis describes all these phenomena where the rate of reaction is influenced, but the substance that is influencing the rate of reaction remains chemically unaffected after the reaction completes. So, catalysts could either accelerate or slow the formation of a particular product species Like in this case, if H2 and O2 are reacting to form water, you could add a catalyst and increase the rate of reaction. So catalyst usually occurs at the fluid catalyst interface, where the catalyst can form a complex with the reactants and products. Like this case where we are oxidizing SO2 to form SO3. So now SO2 and O2 are reacting on the platinum surface, and they're forming this complex, and then they're dissolving and they're giving your product. So we'll go over a brief history of catalysis, where Jacob Berzelius was the one that coined this word catalyst for a series of reactions that he saw over a period of years in the late 18th and 19th century. There's a lot of work on reactions where a substance is added, and that is increasing the rate of reaction. And he also worked on several reactions such as the conversion of starch into sugar in the presence of acids, the decomposition of hydrogen and peroxide in alkaline solutions, combination of hydrogen and oxygen on spongy platinum. And what he observed was that when he added these compounds such as acids, alkaline solutions, and spongy platinum, he was able to increase the rate of reaction. But after the reaction completed, he was able to recover these compounds. So, after going through other scientists' work and his own work, he coined the term catalyst, which increases the rate of reaction but remains unchanged. And this was taken from the Greek words kata, which means down, and lion, which means loosen. So, in the first work of using inorganic catalysts was by Cordius, who worked on using sulfuric acid to increase the conversion of alcohol to ether. And in the late 18th century, a lot of work was done earlier also on the formation of alcohol. But here there was a lot of work on adding substances to increase the rate of reaction. And they established a protocol for beer fabrication. And they saw there that when you added a certain substance, which is known as amylase, the rate of reaction, the formation of alcohol increased, and the speed at which it formed increased. And Willy Kuhn, he suggested that you could call these compounds as enzymes, which were biological catalysts. And the first systematic study of catalytic reactions by metals was done in around 1970, where they used silica or alumina or clay to increase the reaction of ethylene from alcohol and sulfuric acid. Then there was a lot of work on using platinum where as a catalyst, which still today is used as an important catalyst in many industries. So in 1817, Humphrey Davy, he made this non-explosive lamp, which was used in a lot of mining operations then. And he saw that the combustion of coal gas and air in the presence of these platinum and palladium metal wires was possible without the need of a flame. And this was very safe. This was a very important innovation in terms of mining operations where you couldn't use flames. Then several other scientists also saw that they could use this platinum powder or platinum wires to increase the rate of reaction. And still date, platinum is an important catalyst. Then important work for which William Ostwald was awarded the 1909 Nobel Prize in Chemistry was where he investigated reactions that are catalyzed by acid and base. Paul Sabatier was another important scientist who was awarded the 1912 Nobel Prize for Chemistry for catalytic hydrogenation reactions. Dr. Gerhard Hurd also received the 2007 Nobel Prize for Chemistry for his pioneering work on heterogeneous catalytic reactions, and he refined the Haber-Bosch process for synthesizing ammonia using iron, and he innovated it using vacuum technology. Another notable prizes for catalysts were in the year 2001, 2005, and 2011. Current industrial examples where catalysts are used are in the petroleum industry, where they crack these heavy hydrocarbons into lighter hydrocarbons to form naphtha and heating oil. For desulfurizing hydrocarbons for sulfur-free fuels, you can reform naphtha to form lighter hydrocarbons, which can be used to create high-octane gasoline. Or you can do an alkylation reaction where smaller hydrocarbons are combined to form a heavier hydrocarbon to form gasoline. Another thing you could do is do hydrogenation of double bond, add hydrogen atoms and make it an alkane, sorry. And this was done on nickel and palladium and ruthenium. And this can be used to make stable compounds or edible oils. You could do the hydrogenation of aldehydes, RCHO plus H2 to give RCH2OH, and this is done to form alcohols. You could do the selective oxidation to form nitric acid, which is used in fertilizers and explosives. And here platinum and RH, sorry, this is RH cause is used. And you could do also form sulfuric acid, which is used in a lot of industries to dissolve minerals. And you can also form ethylene oxide, which is used in antifreeze or fibers and bottles. So, to understand the economic impact of catalysts, nearly 90% of industrial chemicals that are produced worldwide, they use catalysts within their manufacturing process. And if you think about it, one third of the gross national product of the US involves a catalytic process. And the global industrial catalyst market in 2022 was 21.7 US billion dollars, 21.7 billion US dollars. And you can think about this value. The economic impact of catalysts and why catalysts are very important in a lot of chemical reactions. And most of the material used in these slides was taken from Smith, the chemical engineering kinetics, the chapter 8, and chapter 10 of Scott Fogler, elements of chemical reaction engineering. Thank you.